So, ladies and gentlemen, I'm proud to announce Mr. Shay Chen. Trying to do my best to pronounce your name, sorry. He's the CTO of Hacktivity, an advanced security center of Ernst & Young. And of course, he's a well-known blogger and researcher, for example, in various security tool comparison initiatives. And the title of his presentation is very, very long, so would you please?
So the title of the presentation is called Diviner. And what I'm generally about to present is a new technology for predicting the server-side source code without any actual access to it. That's the basics. So let's just start over. My name is Shay. It has nothing to do with shyness. I'm the CTO of a group called Hacktivity, which is an advanced security center of Ernst & Young. Used to be a privately held company in 2011, but then EY bought us, and I actually have somebody to fund my researches, which is good. I want to share a couple of exciting ideas with you, as well as discuss two main subjects. The first subject is a new set of information gathering attacks called divination attacks, which in general enable testers to gain access to the structure of the server-side memory, the structure of the server-side processes, and even to the server-side source code, all using nothing but black box techniques, without any actual access to the server. The second subject is a new project called Diviner. Called Diviner, which is an OWASP ZAP extension that implements the attack that I just mentioned. So before we're going to delve into the details and explain the mechanics of the new attacks, I want to show you what the end result looks like. What do you gain out of the whole process that I'm going to discuss in the following hour? So what you're currently about to see is a map of the server-side memory in an application that I have tested in advance. Okay? What you can currently see is values that are stored in the database, values that are stored in session variables, in files, in static variables, values that cause exceptions, reflections. You can see all that without actually testing the application. Now, better? Can you hear me? Can everybody hear me? Now good? Didn't expect that. So, as I mentioned earlier, what you see is a map of the server-side memory. And in addition, what you can see in this map is exactly how each parameter in the application affects the rest of the application. So let's assume I'm going to test the login page in an application, and I want to see what the username parameter, how it affects the rest of the application. All I have to do is to click it, and I can immediately see how it affects each and every component in the entire application. Does it cause an exception? Is it reflected in the output? Does it delay the execution in a couple of seconds? Does it change the content or any other behavior that you want to see? All that without actually testing or before testing the application. So there's a problem that this solution solves. Okay? There's a problem. And the problem that I'm talking about is a bit different than the problem which is usually the focus on information security talks. I'm not discussing the consumer or the fact he is not aware of his surroundings. I'm not discussing developers or the fact that they're not aware of security mechanisms that they should implement. My problem, or our problem, is the tester, the pen tester, or more accurately, the limitations of the tester's decision-making process. In order to properly explain what limitations I refer to, let's go over the processes that testers actually do that require them to make decisions. Let's go over the penetration testing process. So during a penetration test, a tester needs to go through several phases, perform several operations in order to cover as much territory as possible, in order to detect as many vulnerabilities as possible. He has to do operations such as fingerprinting, Google hacking, automated scanning, fuzzing, and a wide variety of additional operations. But eventually, at the end of this process, or maybe in the middle, the tester gets to the part in which he needs to perform the main phase of the test, which is manual testing. Nobody actually relies on any automated tool to do the entire job. We need to work ourselves. And it's not like after we got to the manual testing phase, we completed half the job. No, we still have a lot of job to do, a lot of tests to perform. How many tests? That's a good question, if you ever ask yourself. So it depends who you ask. According to OWASP, attacks and vulnerabilities, probably the biggest list I know, there's at least 64 different attacks to perform, most of them on each and every parameter. There's 165 different weaknesses, potential weaknesses, different from each other, okay? According to CWE, there's more. According to WASC, there's 34 attacks, then there's 15 weaknesses. If you add lists such as Wiki or OWASP testing guide, you'll get more and more, you'll add more and more to the pile. So we tried merging all those lists into one unified list that tells us which attacks do we need to test, what do we need to perform. And we got to a list that contained over 100 different attacks. And for those of you who don't believe me, take a look. 100 different isolated attacks that most of them we need to perform for each and every parameter in the application. So let's do the math. Let's assume we're testing a small-sized application, somewhere around 20 pages. And let's assume that we have 3 parameters on average in each page. So if we have to perform, I'm sorry for the math test. It's not going to be long. If we have to perform 100 tests for each parameters, and we have 20 pages, it means 6,000 tests, which is a lot, but let's say we have a time frame of a week or 2, we can pull it off. We can probably perform the most important test, even though it's a lot of tests. But if we take a mid-sized application or something larger than that, we'll end up with a lot more. Let's say we'll take an application of 100 pages, not 20 pages. We'll end up with 30,000 tests. 30,000 tests. Now, I'm pretty sure we can do it in 2 weeks, and in my opinion, you can do it in 2 months. So obviously, in the real world, testers can't test each and every attack manually for each and every parameter. We have to find other ways to solve our coverage problem. So how many testers do we have in the crowd? How many pen testers, white hat hackers? Raise your hand. 2? It's Hacktivity, guys. 2, 3? Okay, you're ashamed. So obviously, testers don't perform everything manually. They use various techniques to narrow down the areas that they should focus on and to cover the rest of the areas automatically. So tools or processes that testers use include experience, intuition, and luck, sheer luck, devil's luck, but obviously those are subjects I won't cover in this presentation. Testers also use automated scanners, or as you all recognize them as web application vulnerability scanners, which are great tools that can perform a lot of tests on a wide range of URLs and parameters. There's fuzzers that present plenty of information for the tester, which it includes responses and behaviors of the application as response to different payloads. And there's information gathering processes that help the tester realize or locate areas that are most likely vulnerable. So we'll be able to invest this effort properly. Now, ask yourself, how many hours have you spent chasing leads in penetration tests that don't exist? Like you found something that looks like a lead that might be vulnerable. You wasted half the day. Eventually, you found out it was nothing. Now, what we're trying to do is solve it in a manner. But the current processes do provide some sort of solution. Although they're good, they contribute to the quality of the test, there are certain limitations that prevent the overall solution from being complete. In order to understand what those limitations are, let's go over the advantages and disadvantages of each one of those tools. Now, let's start with scanners. Automated scanners, as I mentioned, are great. They allow us to perform a wide range of attacks on a wide range of URLs. However, a tester is not a human. A tester needs a pattern that he can recognize in order to detect an attack. A scanner that doesn't have an SQL injection detection plugin can't detect SQL injection attacks. Period. It can only detect attacks it is familiar with. Furthermore, even if the scanner is familiar with the attack in general, its logic might not be good enough to detect each and every specific instance. Not every scanner that can detect cross-site scripting can detect each possible instance of cross-site scripting. So it's good, but it's limited. Fuzzers, on the other hand, do something different for the tester. They execute numerous payloads on numerous amounts of URLs and parameters, and they present the content for the user to make the decision, for the user to analyze. However, they present so much output that the user might be required to spend days and days just analyzing it. So it's good. It's another perspective. It allows the user to use his mind to decide whether or not a location might require or might justify more investment in time. But they provide so much content, and it's difficult to analyze that the contribution, sometimes it's more work than benefit. Again, depending on which tool you use and in which scenarios. Information gathering, on the other hand, is a bit different. It's not doing the work for the tester. It's helping the tester doing its work, doing whatever it is he's supposed to do. Instead of just saying those locations are vulnerable, information gathering processes help the tester obtain leads, information that might suggest which locations are vulnerable so he can test them manually. Now, let's divide information gathering into two main categories. Now, there's passive information gathering, which is generally processes that use non-intrusive means to obtain information. They generally gather things that are out there, such as HTML comments, information from search engines, nothing that really attacks the application. And there's active information gathering processes, which actually include attacks that attempt to extract more information, such as fingerprinting, file and directory enumeration, brute force attacks. But active information gathering also include manual processes that are performed whenever we test any vulnerability. We actually performed some method of active information gathering during the manual assessment phase. For example, let's explain what I mean. Let's say we're trying to see if a specific parameter in a page is vulnerable to SQL injection. We might send something like an input with a quote or a time delay payload and see how the page behaves. The page might respond with an exception, might be delayed, what might have an abnormal behavior, an abnormal content, and we learn from this information that we extracted and decide upon the response whether or not we should invest more time in that area. Now, the problem is, this is a great tool. It enables us to use our mind. In my opinion, probably the most powerful tool in the pentester arsenal to see if a location is vulnerable. It's not limited by patterns. Testers can actually detect attacks they're not familiar with. They can see something suspicious and again go and search more about it, learn more about it, ask a friend or whatever. But this powerful tool, probably the most powerful tool, is only used in specific locations which we test manually. So it means that the most powerful tool we have is not used on the entire applications, only on small fragments. And the less efficient tools we have, without underestimating any one of them, are used on the entire application. So we do our best for a small fragment and the rest for the rest. So we believe that there's a missing piece in the puzzle of penetration testing, that there's a phase that we don't perform that can really contribute to the process. And we believe that this phase is tied up to Mr. Big. Now, I initially tried to force the acronym, the initials, on Miyagi. I did everything I could, but I ended up with Mr. Big. And you all think you know Mr. Big, but do you really? What Mr. Big stands like is massive recursive behavior information gathering, okay? It's a process in which what we do is to collect the information about behaviors that you would have collected manually. So when you test a specific entry point or parameter, you're trying to see if it will behave in a certain manner in response to input. We're implementing a process that collects all these behaviors and presents it to you in a visual manner that will enable you to make decisions based upon this information quickly and efficiently. Now, in order to better demonstrate what it is that we're doing, let's take a look at the following vulnerability. Now, I'm assuming that you all know what SQL injection vulnerabilities are. By the way, apologies in advance. This presentation is designed to be presented to pentesters, security researchers. Anyone not feeling comfortable enough with SQL injection payloads might be confused in several sections of this presentation. Now, an SQL injection vulnerability, just a sample instance, we might send a value that contains a quote to a certain entry point. And if this entry point uses the input to construct a query, then I have a vulnerability that I can exploit. But this specific SQL injection vulnerability is not that simple. What happens in this specific SQL injection vulnerability, it's an indirect vulnerability. It's an indirect vulnerability, which means that the page in which I send the malicious input, let's show it, that's the password recovery page I'm showing. The page in which I send the malicious input does not compose a query at all. However, it stores the value that I send to it. For example, user1 quote. It stores this value in a session variable, which is used by other pages in the application. So in this example, I sent user1 quote to this page, to the password recovery page. It was stored in a common shared variable, a session variable, and another page in the application, the site my page, which uses it, becomes vulnerable because it takes the value from the session and then constructs a query. An indirect attack, not something that most scanners, if not all of them, can detect. Furthermore, to detect an indirect attack manually is a very difficult job if the application is big. It means to test the effect of each and every parameter on the rest of the application pages, which is a lot of work to do manually. However, what I want to show you is a nice feature in Diviner, the project I'm going to expose here, which is called task list. What the task list does, it organizes the behaviors in the application according to interesting behaviors. Now, it's not really, you don't really have a good focus here, so I'll try to explain as best as I could, but as best as I can. But there's a category here called session exceptions, which means exceptions caused by session values that are in the control of the user, meaning the user can affect session values and cause exceptions in other pages. So in this analysis, we can clearly see this vulnerability immediately. We can see that there's a page called phase 2. Phase 2, you have to send the input that contains a quote, and this input affects another page called sitemap. Clearly, simply, without even sending a single payload to the application, I can already see the lead and know where to locate and how to locate and how to reconstruct the scenario that will exploit this complex vulnerability. Okay? Now, furthermore, if I'm able to present the map of the memory, if I'm able to present how each parameter affects the other, I can also execute a nice feature that I'm going to demonstrate now. Anyone ever heard the name clairvoyance or the term clairvoyance? It's a term in French. It means clear vision. So what we meant initially by divination is that we are able to predict something. And what we're currently able to predict is the server-side source code of each and every component. We're actually able to discern and locate specific lines of code that are running behind the scenes in the backend, that are running behind the scenes of each and every component in the application. So before I'm going to explain the mechanics, how do we actually get to that output, let's tell a short story that explains where it was born. So the idea was born in Texas, in Houston. I was sitting with a colleague in a bar called the Flying Saucer, nice plates everywhere, and we were discussing the applications of an attack called connection pool consumption. Now, I'm not going to explain the mechanics of this attack. It's irrelevant. But what the attack does, it delays the execution of a single line of code so that the lifespan of everything defined before this line of code will be delayed. And then it dawned on me that if we manage to perform an attack that delays a specific lines of code, that there's a secondary conclusion. It means that this line of code exists. Think about it. If there's a vulnerability, and I manage to exploit it and prove that it exists, it also means that the lines of code that might have created such a vulnerability exist behind the scenes. So initially, we thought to use this insight in order to convert the results of scanners of various automated tools into code. But then, after we thought about it a bit more, we realized that every behavior the application has, everything, can be converted into code. Even simple actions such as redirect operations or actions such as input being reflected in the output or exception, everything can be converted into code. So in order to actually obtain information that will enable us to present the entire source code, or at least a large portion of the source code of a website, we have to detect enough behaviors in order for us to provide quality content. Now, when I first got into the field of application security, my mentor, a guy called Ofer Maor, taught me that the best type of information that I can disclose is the source code. If I get the source code, there's pretty much I have everything. Because if I get the source code of the application, I know how the application interacts with its various components. I know which technologies are used. I know how the queries are structured. I can locate vulnerabilities in the code by seeing the code without even testing the application. I can get a lot of benefits that testers today, in order to obtain them, need to ask the code in the context of a gray box text, not just a black box test. So imagine you being able to perform a white box assessment whenever you want to, even if the customer is not willing to provide you with source code. You can actually do that. You can get the source code yourself, or a big portion of the source code using this process. You can get information whether or not the developers, your customers, are willing to expose them in order to assist you in the test without them even knowing it. So the process itself can really help us obtain information that can allow us to make better decisions, to invest our time properly in the test. Now, before I'm going to explain exactly how it works, let's see a short demo of exactly what this tool gives us in the context of this application. So I've executed this tool, Diviner, on an application called Puzzle Mall. It's just a demo application, nothing special about it. And what the tool actually did, Diviner is an extension of OWASP ZAP Proxy. For those of you who are not familiar with the product, it's a competitor of Burp. Think about it that way. And in ZAP Proxy, since we test it or use it as an interception proxy, there's a history. There's a history section that stores all the requests and response that we got from the application or sent to the application. Now, Diviner hooks into this history module and attempts to re-execute each and every request that's in there. Now, what happens is that the process itself, it's quite intrusive, but not intrusive as a scanner, enables us to see results about the application that we probably couldn't have gotten in any other way except this process. So we can view the source code of various components. We can see how each parameter in the application affects the rest. For example, by clicking a parameter, I can see that the effects it has on the application are it causes specific exceptions in specific locations, and it's reflected back in the output of other pages, which might suggest vulnerabilities such as open redirect, cross-site scripting, or other behaviors. Now, any questions so far? Okay. Now, in order to properly understand how does it work, what we do, as I mentioned earlier, we attempt to replicate or reconstruct or resend each and every request in the application. So let's assume, imagine there's a history tab with like 20 requests. Request 1, request 2, request 3. What we do is to send an input to the first parameter of the first page and check how it affects the response of the same page. And then send a value to the first parameter of the first page and then checks how it affects the second page. And then send a value to the first parameter of the first page and checked how it affects the third page, and there over and over and over in a recursive algorithm. Eventually, after performing all those operations with authentication, without authentications, with anti-CSRF tokens, without anti-CSRF tokens, using various scenarios, we get a huge bunch of behaviors. Now, on these behaviors, what we do, we have a bunch of behaviors. We're trying to convert those behaviors into various visual representations, source code, memory maps, process connections. And the way we do that, behind the scenes, each behavior can be caused, can be generated by certain lines of code. It doesn't necessarily mean that each behavior has to correlate to a specific line of code. There might be different options. For example, if we have a behavior in which the server replaces a session identifier. It replaces a session identifier in the cookie. It can be several lines of code. It can be a Java line of code such as set header, which replaces the session or replaces a variable in the cookie, but not necessarily kills the previous session. And it can be a line of code such as invalidate, which replaces the session, but also kills the previous session. So in order to know exactly which line of code it is, with a high probability, we verify each and every behavior that we find. So in the example I just gave, what we'll do is actually we'll try and see if the previous session is alive. And if it's alive, we're going to raise the probability that it's a set header line of code. And if it's not alive, we're going to raise the probability that it's an invalidate line of code. Eventually, we'll end up with a bunch of behaviors and probabilities that suggest what is the code behind the scenes with high probability or with the highest probability. And that's exactly what we'll present to the user. Now, like I mentioned, it's not the real code. It's something we predict. We predict this line of code, this source code presentation. It's actually pseudocode. And you can convert it to different languages. If you prefer to see the code in Java, you can do that. If you prefer to see the code behind the scenes as ASP.NET, you can do that as well. So you can see the source code in a manner that can suit your choices. And the best way to use it, let's say I'm going to test a specific page, let's say the login page. And usually I would have sent an SQL injection payload. But using this process, just by viewing the code, I can know whether or not the page actually uses a database connection. There's no point sending SQL injection payloads to a page that uses LDAP. And we can know which technologies are running behind the scenes by looking at the code. So it can help us really perform more efficient penetration tests. Instead of just wasting time throwing payloads that won't work, we can see which payloads are more likely to work. Now, just to clarify, I'm not suggesting to stop working like you used to. I'm not suggesting that you should stop using your intuition, experience, or luck to decide which payloads to execute on each and every entry point. I am suggesting, however, that you perform this process first. It will be much easier to see exactly where the leads are and test relevant attacks and thus trying payloads based on luck or whatever it is you've been using right now. Now, Diviner is an open source project. If you want to get to the homepage of Diviner, simply Google Diviner, Google code. Otherwise, if you Google Diviner, you get to some terrible, terrible series. I wouldn't recommend that, that's for sure. So, Diviner, Google code, you'll get to Diviner homepage. See if it works. Get to Diviner homepage, there's videos that present exactly how to use it. There's explanation, documentation. Soon we will create a wiki that explains which behaviors are converted into which code and also allow you to participate in case you have ideas we don't have. You can also get updates on Diviner from Hacktivity website, from the product page in the Hacktivity website. Okay? And finally, in order to properly install Diviner, in order for it to work, you need ZAP Proxy. Obviously, it's an extension for ZAP Proxy. And you need Java 1.7. Otherwise, it won't work. OK, guys, that's pretty much it. Some future plans we have. as I mentioned earlier, Diviner really excels in detecting leads for indirect attacks, complex attacks that currently automated scanning tools, especially open source tools, can detect. So we're currently cooperating with 2 open source projects of scanners in order to provide them an XML database that will explain which scenarios the scanners need to perform to detect those complex attacks. So the way it will work, you will run Diviner, you will export an XML database, you will load or import the XML database in a scanner of your choice, something that supports the format, and then you'll be able to use the logic of the automated scanner to detect those complex scenarios. It's also good from a performance point of view, since instead of sending numerous payloads from the scanner and overflowing the application, you can actually target the areas that are most likely vulnerable, instead of just bombing the application with millions of payloads. Any questions? Okay, guys, hope you enjoyed. Enjoy the rest of the conference. That's it.